Insomnia. Ever been there? It's like playing hide and seek with sleep, but sleep's just not really into it. Instead of counting sheep, you end up counting the hours till morning. There's this whole neurobiology dance involved, cortical arousal, stress response systems, and brain activity that's supposed to be winding down, but decides to throw a party instead. But what is insomnia as a pathology? Well, according to the 5th edition of the Diagnostic and Statistical Manual of Mental Disorders, insomnia is the predominant complaint of dissatisfaction with sleep quantity or quality associated with one or more of the following symptoms. Now, I know this might look like a lot, so let's break it down one by one. Insomnia is characterized by difficulty initiating sleep, difficulty maintaining sleep, early morning awakening with inability to return to sleep, sleep difficulty occurring at least 3 nights a week for at least 3 months. Sleep disturbance must cause clinically significant distress or impairment in social, occupational, educational, academic, behavioral, or important areas of functioning. Sleep difficulty occurs despite adequate opportunity for sleep and is not better explained by and does not occur exclusively during the course of another sleep-wake disorder. It is also not attributable to the physiological effects of substance such as a drug of abuse or a medication. Lastly, coexisting mental disorders and medical conditions don't adequately explain the predominant complaint of insomnia. This poses the question, what exactly is sleep? Sleep is comprised of 4 stages. In stage 1, the transition from wakefulness begins. Brain activity slows down, theta waves emerge, and a person may experience fleeting thoughts or images. In stage 2, they enter a deeper sleep. The brain produces sleep spindles and K complexes alongside theta waves, with sleep spindles believed to play a key role in memory consolidation and K complexes in maintaining undisturbed sleep. The person moves into stage 3, they experience slow wave sleep, with the brain primarily emitting delta waves during this phase. It's crucial for physical restoration, allowing for the body to repair and regenerate. Lastly comes REM sleep, where brain exhibits activity resembling wakefulness. Vivid dreams occur during this phase, as well as muscle atonia, also known as muscle paralysis, preventing us from acting out our dreams. To better understand sleep, we must first understand what puts us to sleep in the first place and what wakes us up again in the morning. Orexin, serotonin, dopamine, acetylcholine, norepinephrine, histamine, and glutamate. These are all neurotransmitters released by the ARAS, known as the ascending reticular activating system. This system regulates cortical arousal and is known to promote wake. But what puts us to sleep? Well, that's where the VLPO comes in, the ventrolateral preoptic area, a cluster of neurons in the hypothalamus that acts as a switch and inhibits arousal. VLPO floods the brain with inhibitory signals. With the help of the VLPO's main neurotransmitter GABA, it floods the brain with inhibitory signals, which inhibits the wake-promoting arousal system. But what does happen differently in an insomniac brain? To be able to answer this question, we must first understand the architecture behind an insomniac's brain. One of the key structures is the pons, a region in the brainstem orchestrating eye and facial movements, contributing to REM sleep onset, and experiences global deactivation during non-REM sleep. However, in insomniacs, the pons seems to be hyper-aroused. The heightened activity in the pons disrupts the initiation and maintenance of sleep, keeping the person in a constant alert state. Moving on to the thalamus. Think of it like a central processing unit for sensory information. Insomniacs have an altered thalamic response, which can lead to an increase in sensory processing, meaning that when sleeping, the brain might become more sensitive to various stimuli, leading the insomniac brain to overreact to environmental factors, making it challenging for them to fall asleep. Now for the frontal cortex, often termed as the cognitive hub of the brain, playing crucial functions like working memory, problem solving, and evaluating situations. When it comes to an insomniac brain, the frontal cortex may experience irregular activation in specific areas. This is known to trigger anticipatory anxiety. Additionally, reduced activity in the inhibitory regions of the frontal cortex can lead to persistent rumination and trouble silencing the mind. This makes it very difficult for individuals to unwind and fall asleep. Lastly, we're going to take a look into the neurobiological abnormalities of an insomniac brain through 3 separate measures: neurophysiologic, neuroendocrine, and neuroimaging measures. Studies show that insomnia patients exhibit increased cortical arousal, more specifically beta and gamma frequencies, which are linked to active mental processing during wakefulness, supporting the understanding that those with insomnia have challenges ending mental activity during sleep. Activity leads to sleep state misperception known as paradoxical insomnia, characterized by a person's significant overestimation of the time it takes them to fall asleep and underestimation of the total duration of their sleep. Continuing on, insomnia is linked to chronic activation of the stress response system, particularly in the pituitary gland. This is directly linked to higher levels of cortisol, norepinephrine, and other stress-related markers. Lastly, in neuroimaging studies, PET scans observed a different metabolic process in the bodies of insomniacs, where they found increased global cerebral glucose metabolism during wakefulness and NREM sleep. In MRI studies, insomnia was found to be accompanied by a reduction in gray matter volume, predominantly in the hippocampi, making an interesting link between sleep deprivation and memory. Studies using the proton MR spectroscopy suggest that lower GABA levels were present in the brains of insomniac patients. This makes a very important connection to what we saw about the VLPO. This concludes the journey inside an insomniac brain. Thank you for watching, and I hope you enjoyed.